I could rate all, let me give myself some more room here. If RA, which is a function of all the concentrations, if I could write all the concentrations in terms of Na, and if I could write the temperature in terms of Na, then I can solve this equation. Now this is a special case, I can't always do that. I can write all the concentrations in Na if the stoichiometry allows me to. And we'll see exactly what that means. If I could write all the concentrations in terms of one of the concentrations, effectively. And that's if the stoichiometry is sufficiently inflexible. How about T as a function of Na? Well, there are two types of situations. I could run a reactor that's isothermal, that is where I keep the temperature fixed by external means. I attach it from thermodynamics. How do I keep the temperature fixed in a thermodynamic system? Don't ask me to repeat the question. Volunteer?
Run it adiabatically.
Adiabatically is insulated. Temperature can go up, temperature can go down. How do I keep the temperature fixed?
Change the phase.
Did you take thermodynamics? Who taught you thermodynamics? Thermo 1, not Thermo 2.
Professor 2.
Professor 2. I'm going to have a talk with Professor 2. How do you maintain thermodynamically a system at fixed temperature? A heat sink. What is a heat sink?
It's like, let's say if you want to keep, for example, a drop
Close. It's not exactly what I was looking for, but that's close. Did anyone pass Thermo 1?
If you have a phase change, you have to
And I don't even like thermo, but this is...
During a phase change, the temperature is constant.
What if you're looking at a system that's not at the phase change of the material? If you're dealing with water at atmospheric pressure, you can only work at 100 degrees C? That's not good enough. Yes? Even the graduate students don't know this? Far too complicated for thermodynamics. Not chemical engineering, thermodynamics. What is the basic concept in your first week of thermodynamics for maintaining constant temperature? They vary, but if you want to keep the temperature constant, what do you do? Theoretically, what do you do?
change the volume, specify the pressure, then you have a variance in the volume.
That's an equation of state. But how do you maintain the temperature fixed? Okay, at the Thermo 1, you contact your system with an infinite constant temperature reservoir. That's the basic first chapter of any thermodynamics book. You presume that theoretically you have these infinitely large systems of constant temperature, and if you contact your system with that, then if your system, the temperature goes up, it transfers its heat to the constant temperature reservoir. Since it's infinite, that doesn't change the temperature of the reservoir. Okay, so one way where T could be a function of Na is if T is constant, and it's trivial. Another way, there's an equation, another equation that relates the temperature to the concentration. What equation is that? Volunteer? Volunteer means I haven't said it before, or it's not totally trivial. When I go around the room, it means it's totally trivial. What equation relates the temperature to the concentrations, and of course the volume? It's an equation of state, but what other equation do I need? Typically I need more than one equation because I have more than one variable. How many people took 228? How many people passed 228? So what is the title of that course? Okay, that's the new title. The old title. What equations do you do in 228? Did you, over the summer, you formatted the hard drive? Did anyone, come on, this is Monday morning, gotta get a good night's sleep, Sunday night. What equations do we need?
Conservation.
Hmm?
Because I know the name beside the ideal equation is
The ideal equation, I don't know what the ideal equation is.
EV equals NRT.
That's an equation of state, we already said that, that's not what we're talking about. Okay, this, you're not making a good impression here. What is the other equation of 228? And what else? What else? Mass conservation doesn't have temperature.
Energy conservation. Energy conservation.
The energy equation. The energy equation would relate the temperature and the concentrations. If a reaction proceeds, there's a certain heat of reaction. It either liberates or takes in heat. If you know the heat capacity of the system, that changes the temperature. So, at we're going to begin the semester, this early part, where we're going to presume that the temperature is fixed, that the system is in contact with a constant, infinite constant temperature reservoir. Later on in the semester, we're going to use the energy equation to allow the temperature to vary. Right in the beginning, we're going to just assume it's fixed. But this is the formula for the integral method of analysis. Now, we're going to start out with certain assumptions, and as the semester goes on, we're going to take away those assumptions. So we're going to assume a number of things. We're going to assume 1, isothermal. 2, single reactor. 3, single phase. 4, constant density. So for this initial analysis, I'm going to make these 4 assumptions. By the end of the hour, or maybe the next hour, I'll remove the constant density assumption. But generally, you start simple, and then you make, once you understand the simple case, which often isn't that simple, then you can make it more complicated. If you put all the computations in the beginning, you never get anywhere. Okay, so what happens? Constant density means V doesn't depend on NA. So V is just a constant under this assumption. And then V can go into here, and I'll just get a dCA. So this implies that dNA over V is just dCA. If I do not have constant density, this is not true. It's only under this assumption. Isothermal means T of Na is just T. Or if you like, why don't I write it this way? T is not a function of Na, just fixed. Okay, so under these assumptions, I have dCA over Ra from Ca of 0 to Ca of T is equal to T. And that's the equation for the integral method of analysis under these assumptions. So, and of course, what's the idea here? If I have a single reaction, if I have single reaction, actually let's call that 5, single reaction. If I have a single reaction, then Ra is just K of T times F2 of C. If I had multiple reactions, then I would have a sum here. But if I only have a single reaction, then Ra is Kf2 of C. And this becomes the integral from Ca of 0 to Ca of T, dCA over F2 of C, which hopefully can be written as a function of Ca over, is equal to the integral, well, is equal to K of T, dt, K of T, T. So under these 5 assumptions, this is my equation, and in principle, I would now integrate. What would I do in an experiment? I have a batch reactor. I started out at some initial concentration. And I keep measuring the concentration at many different time points. So I measure CA of T. And then, remember, F2 of C came from a guess. I had a guess at a mechanism. So this is an analytic quantity. I integrate this. And what I would plot is I would plot CA of 0, CA of T, dCA over F2 of C versus T. Again, what do? I'm measuring the concentrations as a function of time. And then when I integrate this, I have some function of the concentrations, some function of CA. The answer is a function of CA of T. So that I plot that quantity, that function of CA of T with the measured CAs versus T, and hopefully I will get something that looks like a straight line with the slope K. If I get that, that means this mechanism is adequate. If I don't get that, it's not adequate. So let's do a simple example. Do a couple of examples. So example 1. Let's say my mechanism is A goes to product, elementary. A goes to products elementary, so I have to write, so what is Rn? Who was I up to? I think this the next row. Yes? FP? Concentration of product. Concentration of product. I have no idea what you're talking about.
One would be ENADD.
Yeah, but I'm looking for the constituent equation. What's the constituent equation? The right side.
K times
K times
concentration
KCA.
rate. Okay.
If you don't understand this, then you haven't learned anything this semester. 0. Okay, so let's plug in. So K, so what is F2 of C here? What is F2 of C? Minus CA. Okay, so now I have dCA over minus CA, CA of 0, CA of T. What is that integral? Shouldn't be a shock. She had the last question. Ln of what? Log of CA from CA of 0 to CA of T is equal to T, KT. And I have a minus sign. So I'm going to move the minus sign to the other side, and I get CA of T over CA of 0 is equal to e to the minus KT. I move the minus sign to the other side, I exponentiate it, where I have CA of T is equal to CA of 0 e to the minus KT. So that's the answer for first order reaction. And you've seen first order reactions before. In freshman physics, you spoke about radioactive decay, which is presumed to be a first order process. And the amount you have at any given time is what you started with times e to the minus KT. And K is 1 over the half-life in radioactive decay. Well, K is related to half-life. It's not 1 over, it's a constant time set. We'll talk about half-lives in a few minutes. Let's look at a couple of other examples. Let's say I have a 0th order reaction. This is called first order. And remember, what did we say order means? What is the order of a reaction? What's your name? I'm sorry. What's the order of a reaction? Yeah, you have to keep telling me your names again. So, I can hear you. The stoichiometric? What is stoichiometric? It's related to the stoichiometric, but it's not the stoichiometric. We spoke in detail about how you measure the order of reaction. So what is the order of a reaction?
It's the sum of the stoichiometric coefficients.
That's only if I have an elementary reaction. What is it, the order of reaction? The exponent of in the rate expression. So it's the sum of the exponents of the concentrations on the right side. So what's the order of this reaction? 1. Okay? So that's why we call this a first order reaction, because the sum of the exponents is 1. What do you think I mean when I say a zero order reaction? Constant, 1. Constant 1. A full sentence. What is constant 1 to 1? CA to the power 0. Okay, so that says that if I have some reaction, say A goes to product, and my rate expression is just minus K, CA to the 0. Is this an elementary reaction? Why? I always represent reactions according to stoichiometry. Stoichiometry is bookkeeping, not kinetics. And order of reaction is kinetics, not stoichiometry.
I see the stoichiometry is just one. It's not, gravity is not. So I assume
There's no change.
There's no change with reaction. No change in what? Then there's no reaction. That doesn't make any sense. There's no if you say there's no change in concentration, there's no reaction.
According to the 8 rules that we have to determine
It's 8 rules plus common sense.
plus common sense. So the only thing we know right now is that the order reaction is an integer, so that gives us a clue that it is it's a elementary reaction. And so, and the rate is constant. It doesn't change because.
What did we say about the order of about an elementary reaction? Yes.
The order of the reaction has to be equal to the stoichiometry.
If
It is elementary.
is that the case here? No. Thank you. Somebody looked at her notes. So this is clearly not elementary because the coefficient here, the stoichiometric coefficient, is not the order of reaction. So it's not elementary. But nevertheless, experimentally we determine it. So we go through, what is F2 of C here then? In this case. Next to her? I'm sorry, 2 next to her. Why not? CA to the 0, so it's just minus 1. It's the minus. Okay, so that says I have minus dCA from CA of 0 to CA of T. dCA is equal to KT. What's the integral here? You just answered, so I'll let the next one.
CA.
CA, so I have CA of T minus CA of 0 is equal to minus KT. Or I should write the other way around, CA of 0 minus CA of T is equal to KT. So here again, I would plot CA of 0 minus CA of T versus T, and hopefully get a straight line of slope K. Now, I want you to notice something. Is it possible that this rate expression is going to be valid over all concentrations? Is that possible? And what? Tell me why. Volunteer? Is it possible that this rate expression always holds for all values of concentration? Is that reasonable? So we have a volunteer?
When the reaction is finished, so it can be possible because when everything is used, you can't have a reaction.
Right. So if this were always true, then even when I had no CA, I would be depleting it and I'd get negative concentrations. So I can't have that. So clearly there's a certain concentration range where this might be plausible, but it's not plausible in general. Let's do one more example. Let's look at an nth order reaction. Nth order is, say I have Ra equals minus K Ca to the n. So what is F2 of C here? Who's the next person? Minus Ca to the n. Okay, so I'm going to just automatically bring the minus sign to the other side so I don't have to worry about it. So I have minus Kt is equal to the integral Ca of 0 to Ca of t dCa over Ca to the n. What's the integral of Ca to the minus n? I'm sorry? What is the integral of Ca to the minus n? Higher mathematics. Ca to the minus n plus 1. 1 minus n. Is equal to minus Kt. Okay, so here we have a few examples. And we'll use these examples in a few minutes, but I would like to introduce another notation that turns out to be useful for a lot of these problems. So I think it's sort of straightforward how to do this. And let's look at a piece of notation that's sometimes useful. It's sometimes useful to introduce notation that's equivalent to the concentration, or equivalent to Na. And that is called capital X, not to be confused with little x that we used a week ago for the extent of reaction. This XA is the fractional conversion. The fractional conversion